welcome to all of you in the next class of this course. So, now let us recall what we have done in the last lecture. We have implemented various algorithms under different category of a methods like Adam-Bashforth, Adam-Waltons, Nystrom, Milne-Simpsons. Under these different categories, we have implemented the example of one particular linear initial value problem. And today what we will see how to solve a system of differential equations with the help of explicit and one implicit method. So, based on that we will conclude that what is the advantage of explicit method. That is the aim of today's lecture. Okay. So, let us take the same example which we considered in one of our lectures, which is here y double dash x plus y is equal to x. Okay. So, we have to solve a second order differential equation. So, we are converting it to the system of differential equations which we have already seen earlier. U dash is equal to v by assuming u is equal to y and v is equal to y dash, which you can also see from the slides which we have already seen in the lecture. Okay. And now, so basically we are trying to implement this system of differential equations. So, let me open the Octave. So, this is the code which we have implemented. So, here the particular value of this initial conditions alpha and beta what we have chosen here is 1 and 2. So, again we have chosen two variables a and b because a is 0, b is 1 like we were doing in case of a linear initial value problem. And in this case we have also chosen n is 1000, okay. H is b minus a, again we are creating a array of x a colon h b. You are already familiar with these things now. So, and then okay. So, initial conditions we have implemented u1 is equal to 1 and v1 is equal to 2 because in MATLAB indexing does not start from 0. Okay. So, now let us first look at with the Adams-Moulton method. We are also writing one another function here tick tock. So, tick is here, okay, and tock is at the end of the file which you can see from here. You can see more about this function by in a Octave by typing help tick, okay, which I can show you if you want. Help tick. In a, so basically tick is a inbuilt function from the file which basically tells you about the total elapsed time, okay, wall clock time. So, basically it will tell you how much time is taken by your program. So, total that part of the program where it is ended with talk, which you see here, talk is here and at the initial we have typed tick. So, it will tell you total elapsed time of a wall clock. Okay. So, now we have chosen Adam-Moulton's first category of Adam-Moulton's method which is a trapezoidal method. So, which is a single step, so which is self starting as well. So, I do not need to worry otherwise for a two step method this is a drawback. Okay. So, now if you look at what will be the, which we have seen here also, what will be the algorithm if this will be your un plus 1 is equal to un plus h by 2 Vn plus 1, Vn plus 1 is equal to Vn plus h by 2 this. So, we have already seen the algorithm of trapezoidal method in the case in earlier lecture. So, now the thing is we are trying to implement this. So, now if you look at n plus 1 terms are also involved in the right hand side. So, basically we ended with a system of differential equations of 2 by 2. So, for that reason basically we are ending with this, if you look at un plus 1 is equal to un plus h by 2 Vn plus 1, and so Vn plus 1 is equal to Vn plus h by 2 xn plus 1 plus xn minus un minus 1 minus un. So, basically I can always write in the following way. Some matrix, okay, some right hand side, or I can say it as a B. What will be A, you can figure out yourself, and that is what we have implemented here. A is 1 minus h by 2, at least in one case first row I can match, because this equations will become un plus 1 minus h by 2 Vn plus 1 is equal to something. So, that is why this has the first row of this matrix will become 1 minus h by 2. Similarly, we can go for a second row also. So, this will become h by 2 un plus 1, of course, this should be 1 here, plus Vn plus 1, okay. Rest terms you can collect in the right hand side yourself. So, what will be the first row? 1 minus h by 2, second row will become h by 2 1. So, this will be our matrix A, which we have implemented here. A is 1 minus h by 2, next row h by 2 and 1, okay. And similarly, we can collect the right hand side B, and finally, what is the uses of this slash operator in a MATLAB? Not MATLAB, in Octave. In fact, in MATLAB also, if some of you are having a MATLAB, that is what I have already explained earlier, that you can run the same codes in MATLAB. So, slash operator, the application of this slash operator you must have seen already in earlier lectures. So, this is used to solve a system of algebraic equations. So, in this case we are ending with a 2 by 2 system, which you can also see, because the size of A will be 2 by 2, okay. And after solving we can get un plus 1 and Vn plus 1. So, now let me run this code. Yes, now it will work. Elapsed time is, what we see now, elapsed time is 0.0638, okay. And now, so for a moment I am removing this command CLC, so that earlier time is also clear to you. Screen is not cleared, and so now let me take out this comment from all the steps of Adam-Bashforth algorithm, which we have implemented here. And let us comment all of them, okay. In fact, this A also, yes. So, now if I give the run command, you will see that what is the time, 0.05 with the explicit algorithms, Okay. So, of course, there is a difference in the elapsed time, but that is very marginal, and this will become very significant once you take more points. Let me add 2 more zeros. So, it means we are dividing in, so this is 1 lakh points between 0 to 1. Okay. So, now you will see that what is the time taken in Adam-Bashforth method of second category, because we are comparing both the methods of same order. That is why I have chosen here this as a Adam-Bashforth method of second category of Adam-Bashforth, which is the 2-step method as well, and for that reason it is not self starting, and that is why we have implemented U2 and V2 with the help of a forward Euler method. So, of course, it will take some time here. Elapsed time is 5 seconds. Okay. Roughly it is 5 seconds, which is very much visible on the screen. Now, again, so this is with Adam-Bashforth method, and now, okay. So, again let me comment all of them. And uncomment the portion which will implement Adam-Moulton's. Yes. So, again the total number of discretized points n remains the same, and this time Adam-Moulton's method of second order. Yes. Okay. So, again let us wait how much time is taken by Adams-Moulton's. So, of course, now you can see the difference. The time take 1 second difference, even as you will keep increasing the n, okay, as you will keep increasing the n, the difference will be more significant. Okay. For a small n it is a very marginal difference, but it becomes very significant once you increase the n. Okay. And in fact, this is a 2 by 2 system. If you have to solve a nth order differential equations, in that case you will end up with this algebraic system of order n. N can be more than 2 also in case of nth order differential equations. So, in that case, in fact, the time which we are saving with the help of explicit scheme is very significant. So, in that sense you can appreciate the beauty of explicit methods, because you do not need to solve a algebraic system. Okay. So, that is what we have learned with the help of following example. Okay. Of course, if you wanted to look at the exact solution of this differential equation, that also you can see, because I have already here I have not written, but you can find out the solution of this system also very easily. Okay, and you can plot and you can see, you can also compute the error like we have done in the case of a linear differential equations. You can play the same thing, you can also verify the order of convergence, but here my aim was just to tell you the comparison about the timing. So, the total time taken by implicit method is higher than total time taken by explicit method in case we are solving a system of differential equations. Okay. That way we can appreciate that implicit method is better than explicit method in that sense. Okay. So, now the same stuff or we can also do in case of a non-linear problem. Okay. Same stuff I mean to say that we will here also we will try to solve a non-linear problem with the help of a explicit and implicit methods, and in this case we will also conclude that implicit method is taking more time than explicit method. So, basically explicit method is better than implicit method. So, here the right hand side is 2y 1 minus y. So, this is the non-linear differential equations which is you can see from here, and we have started initial condition from 10 which is 1 by 5, because here we have written the domain x is greater than 10, and the exact solution of course explicitly also I have written here yx is equal to 1 this. So, I in fact I have also implemented this exact solution in this case. Okay. So, y1 is 1 by 5, h again we are working with 0.001, x is 10, h is 11. Okay. So, initially we have implemented exact solution, and then this is again trapezoidal method. So, here also you can see how basically in trapezoidal method we are working, because if you remember the algorithm of trapezoidal method will be this. Okay. So, this is the right hand side which is 2y into 1 minus yn plus 1 plus 2 yn into 1 minus yn. So, this is contrary to the explicit method, where in the right hand side you do not involve any term which contains n plus 1th terms. So, you are ending with a non-linear difference equations, non-linear difference equations. Okay. So, that non-linear difference equations we will be solving with the help of inbuilt MATLAB function fsolve. Okay, fsolve. So, of course, whenever you solve any non-linear equations, you have to start with some initial guess, and that is the case with Newton-Raphson's method also, if you remember from your previous lectures how to solve a non-linear equations. And basically fsolve is a inbuilt function in Octave as well as in MATLAB, and it implements Newton-Raphson's method. Okay. So, I am taking the help of a fsolve functions, initial approximation 0.1, and now you can see what is the time taken by implicit method in this case. 3 seconds. Okay. So, again let me commence this. Again I am removing the CLC command. So, the previous time computed should also be visible to you on the screen. Now, let us see how much time is taken by explicit method. So, you can yourself appreciate the beauty. The time taken by explicit method is 0.088 seconds, and the time taken by implicit method is 3 seconds. Okay. And of course, this is the difference. In fact, if you are solving only one nonlinear system, okay, one nonlinear system of order 1, or you can say nonlinear equation, just one. Okay. In fact, if you have to solve a system of nonlinear equations by implicit method, you can imagine yourself how much time difference will be there. So, of course, explicit method is also better in solving nonlinear equation in terms of computational efficiency. Okay. So far we all are convinced that explicit methods are better than implicit methods. So, it means no one is going to use implicit method, but it is not the case. There are some disadvantage of explicit methods as well, that I am going to cover now. Okay, so here what we see, the definition of a convergence of LMM. LMM stands for linear multi-step methods. So, the study of convergence for LMM involves the following way: yxn will converge to yx dash as n tends to infinity and dash tends to 0 in such a way that this is the case. Okay. So, thus convergent method generates numerical solutions that are arbitrarily close to the exact solution of initial value provided that h tends to 0. Okay. So, we shall assume that all linear multi-step methods which we have seen are convergent, that is they are consistent and 0 stable. That is also we have seen in earlier lectures with the help of one theorem, that consistency and 0 stability implies convergence. Now, we begin the investigations into behavior of solutions of linear multi-step method when h is not arbitrarily small. Okay. So, that is what we will look at with the following example, which is again an example of initial value problem where initial condition is 100. Of course, this is a non-homogeneous, and the exact solution of the problem is also given by this formula. Okay. Turning now to the numerical solutions, Euler methods, forward Euler. Whenever we do not write anything specific in front of a Euler method, this is forward Euler. Forward Euler method applied to above initial value problem will give the following difference equations. Okay. So, this is how the exact solution of initial value problem, that also we have plotted here, and I have also implemented this algorithms in Octave, which you will see later on. So, of course, initial condition is 100, that is why y0 is 100, and forward Euler is an explicit method. So, we are ending with this difference equations. Yes. So, now you will see that how forward Euler behaves for the following example in case of a different h, because the leftmost figure represents the solution corresponds to h is 1 by 3. In middle we are plotting corresponds to h is equal to 1 by 5, and in the rightmost figure we are plotting with respect to h 1 by 9. So, red line shows the exact solution and blue line shows the numerical solutions. So, you can see there is some problem with the forward Euler method when I am choosing h 1 by 3, okay, and that problem is not very much severe in case of a h 1 by 5, and that problem has completely gone in case of a h 1 by 9. Okay. So, what is the moral of all these three figures? That there is something wrong when I am choosing h is 1 by 3. Okay. So, and as I am choosing a smaller value of h than 1 by 3, that problem is not visible. So, it means I should work for a very small h. Okay, I should work for a very small h. That is the conclusion of these three figures. But what that small number should be? What that small number should be? Of course, in this case we have done with the hit and trial 1 by 3, 1 by 5, 1 by 9. Okay. But otherwise, how will you come to know that for which h your forward Euler is working fine, for which h it will not work? So, there is a theoretical concept of uh, absolute stability, which you will see in some advanced course on numerical solutions to initial value problem. Of course, as far as this course is concerned, I am just giving you the motivations. I will not cover the entire detail about this absolute stability concept, okay. But my aim is to tell you that, okay, in some sense implicit methods are better than explicit methods, because they do not give you any restrictions on h as the restrictions which you see in explicit method in the following case. So, that is the whole idea, because this is the last lecture of this course. So, my aim is that to tell you one advantage of implicit method as well, and that advantage of implicit method is that there is a no restriction on h, and how to choose that restriction is a matter of advanced course of numerical solutions to initial value problem, which you may learn in later point of time. Okay. So, here again the same thing, the leftmost graph in figure 2 where yn versus xn is h1 by 3, the numerical solutions has some oscillation which is visible from the figure as well, which are increasing with time, showing the numerical instability. Of course, this is 0, 1, 2, 3, 4, 6. So, in fact, these oscillations grow with the time. The numerical solution is not in agreement with, which is very much clear from the figure. Reducing h to 1 by 5 has a effect on the solution. It now decays in time while continuing to oscillate until about x is greater than 2, and later on it decays. That is very much one could observe from the middle figure, after which it becomes a smooth curve. When h is further reduced to 1 by 9, the solution resembles with the exact solution, but the solid and broken curve do not becomes close until 0.5, which is also visible from the rightmost figure. So, in fact, if I will work for a smaller value than 1 by 9, my solution will be more closer to the exact solution. Okay, that is our intuition, and which will be the case, So, that also we can see with the help of one code. Yeah. So, here basically I have tried to implement this code. So, again in a comment box I have written what is the initial value problem we are going to solve and by which method. Okay. So, again I have implemented initially forward Euler, exact solution also I have implemented, and then you will see okay. So, here just let me I am typing some random thing FDF, so that my code stops here. For initially I wanted to see the results of forward Euler h 1 by 3, okay, which is the leftmost figure should come, because this corresponds to h 1 by 3. Yes. Of course, this is just x label and Y label. So, that is there is some problem with this command in the octave. It will run very in a similar way with MATLAB. So, yes, okay. So, you can see some oscillations are there. That is what we are saying, that numerical solution is not in agreement with the exact solution, and these oscillations are increasing with respect to time. Okay. So, just we have implemented simple forward Euler, and now if I choose H 1 by 6, now if I run my code, okay. So, this is again the same figure, middle one, okay. So, of course, oscillations are less in this case because we have chosen a smaller h. Of course, 1 by 5 is smaller than 1 by 3, but still there are some oscillations. So, let me work out with in fact more smaller value of h. Let us take 1 by 9. So, yes, so we threw, that is what we got the rightmost figure. Okay. In fact, as we could observe from the figure that we do not see very close agreement with the exact solution. So, blue line indicates the numerical solution and red line indicates the exact solution. So, we do not see very close agreement before time 1 or let us say close to 0.5. So, in fact, that is our intuition that if I really work with a very small h, let me arbitrarily choose h is 1 by 90, then what will be my solution? Yes. So, it is in close agreement. So, our intuition has become true that in case of a forward Euler method, we have to work for a very small h for some specific set of a initial value problem. What is that specific set of a initial value problem, and what is that condition based on what we can choose the h, that is a matter of advanced course of on this topic, which I have already said earlier. But here at least you can get convinced that when you are applying a explicit method for some specific problems, you have to be extremely careful because you should work out with a small h, okay. Because by chance if you work for a h 1 by 3 in this case, you will not get the numerical solutions exactly, okay. So, now okay, that is what I have said about explicit methods. Now, let us see how implicit methods works for this example. Okay. This is again, if you want, you can also compute the error, though I have not implemented those errors formula in the octave code, but that by this time you must have learned, you can do it yourself. But here let me show that this is the global error associated with the solution of the initial value problem, which we have considered as an example using Euler method and the backward Euler method. So, this is with the implicit method and this is with the explicit methods. So, of course, this is green line will be corresponds to h 1 by 3 and then h 1 by 5 and then h 1 by 9. Okay. So, in case of h 1 by 9, of course, error will tends to 0, which we have we have observed otherwise also. So, in figure 3 basically we plot global error on a log linear scale. The linear growth of global error on this scale for h 1 by 3. So, this green line corresponds to h 1 by 3 suggests that it is exponential growth which is not acceptable. So, in contrast for h is 1 by 5, the error decays exponentially over the interval 0 to 4, where it reaches a level of about 10 to the power minus 3, and for h 1 by 9 there is a more rapid initial exponential decay of the error. So, h 1 by 9 is acceptable. In fact, I have also shown you the results by choosing h 1 by 90 just arbitrarily. You can also plot the error corresponds to that because the exact solution is in front of you. So, what we observe that Euler method suffers a form of instability for this initial value problem. Of course, this is also problem dependent. It is not that forward Euler method will, when you will choose some h for a forward Euler method, it will not work for all set of a problem. So, this is also problem dependent initial value problem for this particular initial value problem. Okay, so, Euler method is of no practical use for problem with exponentially decaying solution unless h is small f enough. So, exponentially decaying because this is the behavior of a exact solution of this initial value problem, what we could observe because y dash is equal to minus 8y term is there. So, because of that if you look at the exact solution of initial value problem, that is in the nature of with the exponential, okay, exponentially decaying solution unless h is small enough. So, it is not that Euler method will never be used or it is a bad method. You have and that is the aim of this part of the course also. You should learn that which method you should choose for which problem. Okay. Of course, as I also discussed in previous two examples when we were solving a system of differential equations as well as non-linear initial value problem, that implicit methods are taking more time as compared to explicit methods. In this case, what we have seen that explicit method is not performing well when I am choosing large h. So, one can question what is the harm if I choose a very small h? What is the harm? The harm is that computation will be more if I choose a small h. Computation will be more. That is why we should not take excessively small h as well as. Computation will be more, okay. And once computation will be more, your machine's error will grow. That also I will explain you with the help of one diagram, okay. But so this is which I said, let me plot the solution of initial value problem as well as the numerical solution of backward Euler method with respect to different h. So, in the left hand side again h 1 by 3, in the middle h 1 by 5, in the rightmost h by 1 by 9 using backward Euler. So, the locant truncation error for forward and backward Euler methods are equal, but opposite in sign. However, the way that these error propagates is clearly different, what we have already observed from the previous figures. So, in the following example, the backward Euler method is much better to that of Euler method since we are able to choose h without having concern with oscillations for larger value of h. That is what the moral of all discussion. And here the remaining task is that so far I have not shown you the analysis of backward Euler in an octave. So, again let me choose h 1 by 3 and comment all the lines which implements exact solution as well as solution with forward Euler. Okay. So, again let me remove this arbitrary FDF which I have just added to terminate the code, and these command also because they are not working in a proper way in Octave. And in fact, yeah. So, you implement backward Euler algorithms and you will see how the solutions look like in case of H 1 by 3, which is basically the leftmost figure which you see in the slides. Okay. So, now let me change H, oh here I have chosen H 1 by 9 because initially I thought I have changed it to 1 by 3, no, but further it has been changed to H 1 by 9. So, this corresponds to 1 by 9. So, in that case it is the rightmost figure. Okay. Now, let me change to H 1 by 6. So, in this case it should, we should end up with the middle figure, that is what we can see. And here if I change it to H 1 by 3, it will be the leftmost figure, where disagreement between the exact solution and numerical solution is more visible. And that is because of because really method is convergent when H tends to 0, but it is not the case that error is growing. Okay. There will be some disagreement here also, but it is not that solution is nowhere close to the exact solution. Okay. So, this is with respect to backward Euler. In fact, if in this case also let me work out with very small h arbitrarily. So, again you will get a very good agreement. Okay. That is what you can observe from the following figure. So, now as I told you, I will explain you why it is not a good idea to work with a very small h. Because let me draw a figure here h. So, here h tends to 0. So, you know when you are working for a very small h, you have to apply more operations, or you have to reach to a point 1 in a more operations, because from 0 to h, h to 2h and then nh which is equal to 1. That is how we have chosen the our grid size. Okay, this is capital N. So, if capital N is very large and h is very small, because okay, nh, so A is 0, this is B you can say, h is very small, you have to do more operations. So, of course, machine error will be more. So, machine error will behave like that. So, this corresponds to machine error. And when, and what is the behavior of a truncation error? Behavior of a truncation error is that truncation error tends to 0 as h tends to 0. So, this is truncation error. So, every numerical method is equipped with these two errors, truncation error, machine error. So, if we are working for a very small h, machine error is large, truncation error is small, but total error is the sum of these two. Okay. So, of course, we should work for a value of h for which somehow balance between the truncation error and machine error, because if we work for a large h, truncation error will be more, if we work for a small h, machine error will be more. So, we have to choose h in a optimal way, and in this case the optimal h is here where the sum of these two error is minimum. Okay, where the, so basically the conclusion is that we should not work either with very large h or with very small h. We should try to make a balance so that the sum of machine error and truncation error is small. And in fact, if you say that there is no machine error, then of course everyone will choose for a very small h, because only truncation error is a which we are getting in numerical method. But any computer machine is not free with machine error. One way of reducing the machine error is that you should always work on higher precision machines, which will give you a most exact computations if you of any arithmetics. So, which is you must have already what are machines errors, how it affects when I grow with number of steps or number of operations, that you must have already studied in some basic course of numerical analysis. Okay. So, with this diagram, which is a crux of any numerical methods, in fact, when you apply to initial value problem and when you apply to boundary value problem as well. Okay. Because in boundary value problem also you have to discretize the derivative in the same way, and then you end up with a system of algebraic equations. But in boundary value problem also this is the way how truncation error and machine error behaves. In fact, when you apply any numerical methods to PD also the behavior of error. So, this is a basically this diagram which we have seen, you should understand very carefully, which is a crux of any numerical methods, because any numerical method is associated with these two kinds of error, truncation error and machine error. Okay. So, with these words let me stop with my discussion, and I hope all of you must have enjoyed this course, and this also this part of the course gives you the motivation why you should study some advanced course as well on numerical methods, and because numerical methods play a very important role for solving a real life problems where exact solution is not available. Okay. Thank you very much.